Good morning, everyone. My name is Michael Cunningham. I'm from Queen's University in Kingston, Ontario, and I would like to welcome everybody to the Macro 2022 meeting in Winnipeg, presumably virtually if you're listening to this talk. I'm going to be speaking today about polymerization-induced self-assembly in this educational workshop lecture, and I'll be looking at primarily experimental approaches to preparing polymer nano-objects using PISA. I have an outline of my talk shown here and the subjects I'm going to cover. First of all, I will introduce what PISA is and how does it differ from conventional self-assembly, and then why is it so interesting and useful. And then I would also like to show you how you conduct a PISA experiment, what factors and scientific principles control the self-assembly process, what determines morphology, and this is something of primary interest to many people using PISA, and finally characterization of how you make nano-objects by PISA. And this will be wound through the body of the talk. First of all, let's examine what's the difference between self-assembly and polymerization-induced self-assembly. And they're certainly related, the key feature being that in a PISA-type process, the reaction is happening and that actually causes the self-assembly. If we look at normal amphiphilic block copolymers, which have been studied for many years, they are generally not fully soluble in any one solvent. So you have often a solvent that could be a good solvent for one of the blocks, but not for both of the blocks, because of their inherent nature that the blocks themselves are very thermodynamically different from each other. If you have a medium that's a solvent for one block and a non-solvent for the other block, you usually get a self-assembly type process into some types of nano-size aggregates, and this results from association of the insoluble units with each other, and then the soluble units stay on the outside of the nano-object and they act as stabilizing moieties. And the size and shape of these self-assembled aggregates depends on a number of factors, including the length of each block, the overall composition, and how the polymer is added to the solvent. So the process you use to induce the self-assembly. For example, it's just a solvent replacement process. What solvents are you using? What's the rate of addition of the solvents? What's the temperature? And so on. And often these structures may not be at equilibrium, depending on how fast the self-assembly process goes, whether or not the polymer chains are capable of rearranging themselves. So it's possible to get structures that are frozen in non-equilibrium morphologies. And this is an illustration from one of Professor Eisenberg's papers that illustrates some of the different types of structures people have seen for the self-assembly process in conventional block copolymers. So the block copolymers are already made, and depending on how you conduct the experiment, you can get self-assembly into a wide variety of different structures, including, for example, spherical micelles, get rods, bicontinuous rods, small and large lamellae vesicles, and so on. Now, in a PISA-type process, you also end up with block copolymers. But you don't start with a synthesized block copolymer and then have the self-assembly procedure happen. Normally you start with the growth of the first block, and the key thing is that that block is soluble in the reaction medium, and this is sometimes called a solvophilic block. And most commonly what's of interest is that that will be water or an aqueous mixture, although people have also used alcohols, alcohol-water mixtures, supercritical carbon dioxide, and less commonly hydrocarbons. Now, once you complete the synthesis of the first block, you now initiate growth of a second block. And the important feature is that that second block is insoluble in the reaction medium. And as the second block grows, the polymer chain becomes increasingly insoluble, and the chains now begin to undergo a self-assembly process. And the key feature of all this is that it's the growth of the second block by polymerization that induces the self-assembly process. And as with the conventional self-assembly using pre-made block copolymers, the size and shape of these aggregates depends on many factors. Now, the first reported work of this was Ferguson back in 2002. They were doing RAFT, ab initio emulsion polymerization of butyl acrylate. It was not called PISA at the time, and it involved, first of all, the formation of a soluble acrylic acid block, starting with a RAFT agent, and then you had formation of an insoluble butyl acrylate block. And once the butyl acrylate block became long enough, the different block copolymers you had in solution self-assembled to form seed particles, and that acted as the basis for the subsequent emulsion polymerization. So why are people so interested in PISA? And if you look at the literature, and there have been numerous reviews in the past few years, which I will show in my last slide, there's a lot of interest in this. And there's a few important reasons. The traditional methods for making amphiphilic block copolymers often require changes in the reaction conditions during the synthesis. Because you have such different behavior of the blocks, in order to effectively do the synthesis, you may need to change the solvents or the reaction conditions to find a reaction environment that lets you conduct both block syntheses effectively. On the other hand, PISA processes by their very nature are intended to be conducted in a single medium, which considerably simplifies the overall reaction process. PISA further allows a one-step synthesis of a number of different morphologies, simply by controlling the conditions of the process. If you're having a more traditional approach using block copolymers with conventional self-assembly, normally more complex methods are required to achieve certain desired morphologies. But there are some additional complexities in PISA. The key thing being that PISA does require compatibility between the reaction medium and the monomer selection. So for example, if you have very highly water insoluble monomers and you're trying to conduct a PISA in an aqueous environment, you may have difficulties getting enough monomer dissolved that you can make the second block. Now, there's ways around that, and one of the most effective routes is to use alcohol-water mixtures or alcohol itself instead of just an aqueous environment. There are many applications of PISA, and if you look at the review papers, you'll get a sense of these, and some of you may have heard of some of these already. Stimuli-responsive materials, biosensors, a very large body of research on biomedicine or controlled release materials, catalysis, rheology modifiers, Pickering stabilizers, and one of the earlier routes, and that was the Ferguson paper I refer to, as stabilizers for emulsion polymerization. And you will often see this work referred to as surfactant-free emulsion polymerization or surfactant-free latexes. What is it that determines the morphology in PISA? And this is an image taken from an excellent review paper from D'Agosto, and it illustrates the basic components of a PISA process. You start with a solvophilic polymer in the blue. You do a chain extension on that with now a second block that is not easily soluble in the reaction medium. And as that second block grows and the whole molecule becomes insoluble in the reaction medium, you can witness a number of different morphologies depending on something called the packing parameter P, which I'm going to get to shortly. But before we get to that, let's just illustrate what happens at different values of P. If P is less than about 1/3, you would typically get spheres formed. If you have P values between about 1/3 and 1/2, you normally get worms forming. See, these are long cylindrical nano-objects. And if P exceeds about 1/2, then you typically get vesicles formed. And let's go into this P factor in a little more detail, called the packing parameter. And it is a ratio of the volume of the hydrophobic segment divided by the product of the area of the hydrophilic segment times the length of the hydrophobic segment. And this ratio, which is somewhat conical in shape, really determines what is the most thermodynamically preferred conformation for the nano object to adapt as it's undergoing polymerization-induced self-assembly. And of course, you may be asking, well, if the second block continues to grow, does the thermodynamically preferred configuration change? And the answer is yes, it does. We'll talk more about that later on in the presentation. What are the factors that influence the packing parameter? The length of each block is certainly one. The type of polymer in each block, of course, is important. The reaction medium that they're in, the monomer concentrations, the pH can affect the configuration depending on if you have pH-sensitive monomers, for example. So if you're using either acid or base type monomers, then the pH can become quite important. Temperature, and in particular, if you have any thermally sensitive materials that exhibit an LCST, and there may be other factors, but think of this as anything that can affect the conformation of that block copolymer and any of the three individual components that make up the packing parameter P. Now, another question you might ask is whether or not the structures that you're seeing are necessarily always pure. So in other words, do you always get all spheres or all worms or all vesicles? And the answer is no, you don't. You can get a mixture. And part of this is related to whether or not they're at a thermodynamic equilibrium, which I'll get to momentarily. But it's very difficult often to predict a priori what type of structures we're going to get, although we know that there's going to be a progression as the second block grows from spheres to worm-like structures to vesicles. This is an illustration of an image from Bayerdenol, and they looked at block copolymers, and this was a diacetone acrylamide and a dimethyl acrylamide, and it shows a map. And people who have done work on these systems will develop a map like this. In some cases, it requires a very large amount of effort, as you can probably imagine, and a systematic variation of the block lengths of each of the individual blocks, and then examination of the resulting morphologies that you get. And you can see, for example, here, if we start on the horizontal axis, as the degree of polymerization increases, you go from having at lower chain lengths of the dimethyl acrylamide block, a combination of spheres and worms, to worms and vesicles in the middle, and finally to vesicles at higher lengths. If you have, looking at the vertical axis now, higher values of the degree of polymerization for the dimethyl acrylamide block, you always get spheres, and that's denoted by this S. And often what we see in these types of systems is that to make regions that are fairly pure, if we look at down around 95 degree of polymerization for the diacetone acrylamide, with where the red letter B is, you get a narrow region where you make pretty much pure worms. But that's a commonly observed phenomenon, worms in particular being in the middle, that the window where you can make pure worms is often quite narrow. Now, to get to this other question that I alluded to earlier, are the structures at equilibrium? And the answer is sometimes. And it really is a question of how fast the polymerization is happening, how fast the chains are growing, and the mobility of the individual chains, their capability to rearrange themselves into the thermodynamically preferred configuration. Remember, as the second block grows, the thermodynamically preferred configuration can change. If you have chains that are flexible, they're mobile, and they're able to rearrange themselves as the second block grows, then you may retain an equilibrium conformation throughout the process. But it's very common that the polymerization happens faster than those chains can rearrange themselves if the chains have a higher glass transition temperature or the monomer concentration is quite low. Both of those will restrict chain mobility, and that's also affected by temperature, of course, and that will restrict and often freeze in non-equilibrium conformations. There are some other processes related to PISA. They're really PISA derivatives. I'm not going to spend too much time talking about them, but just to spend a minute or two to make you familiar with them. We have something called PICA, which is a polymerization-induced cooperative self-assembly. And here the presence of some homopolymer aids in achieving higher order morphologies. So the homopolymer functions as a cooperative function. There is something called PITSA, P-I-T-S-A, polymerization-induced thermal self-assembly. And in this case, you rely on the properties of a polymer that has an LCST. And you can, first of all, conduct your, for example, a RAFT polymerization shown in this slide. You make your block copolymer. And then if you raise the temperature above the LCST, that dramatically changes the solubility in water, or the hydrophobicity, if you like, of one of the two blocks, of the block that has thermal sensitivity and thermal responsiveness. And you can induce changes in morphology and the self-assembly process using temperature instead of just the polymerization component on its own. There's two other related processes I won't go into in detail, but just to round out your introduction, polymerization-induced electrostatic self-assembly and polymerization-induced hierarchical self-assembly. Now, one of the attractive features about PISA is that there are a number of functional nano-objects that you can make. And this is really the key driver for a lot of the work that's been done using PISA, is the ease of introducing a very wide range of functional groups in either of the two blocks, or both of the two blocks. And in particular for stimuli-responsive materials, for example, for sensing purposes, or in any application where you want to induce a morphology change, inducing functionality is very helpful. You can also potentially induce functionality through the initiating group, and this has been particularly well exploited for RAFT and for ATRP. But the functionality can also come in through, as I mentioned a minute ago, either in one or both of the monomers used to make the blocks. And the range of functionalities you can use quite broad: epoxy, amines, disulfides, thiols, amino acids, azobenzenes, various fluorescent groups, and so on. So almost anything that you might want to put on that chain, as long as you can easily get that onto the backbone, or it's a side chain to a monomer unit, so it goes into the backbone of the polymer unit, then you can have this functionality built in. And another very useful purpose is to freeze in the morphology by cross-linking either the core or the shell, or if you like, the inside or the outside of the nano object that you're making. In this image here I've got from Leonol, it shows what happens when you, first of all, for example, have a controlling group with an initiating group. So this would be, for example, a reversible deactivation radical polymerization controlling group with its initiating group here. You first of all introduce one functional comonomer, simply doing an RDRP type process in solution, and then you can do a PISA process, for example, either an emulsion or dispersion, to give a dispersed phase system, and you can introduce a second functional monomer here. So we have two functional monomers illustrated by either yellow or red. Okay. And you can come up with a self-assembled nanostructure like this, where you have various functionalities in both the core and the shell, and the color coding corresponds to what it is that's functional. So the yellow, for example, functional comonomers, you may have a reactive shell and a functional shell. Remember, these chains are still living, so they can often grow. And the same goes for both the core, in terms of introducing reactivity and functionality. And we had the blue and purple initiating controlling groups, which may themselves also have functionality. So you have a really flexible design strategy for introducing functionality wherever you would like it within the self-assembled nano object. Let's speak for a minute on stimuli-responsive nano-objects. This is an area that's seen a very large body of research conducted. And this, for example, might include pH, temperature, light, oxygen presence, CO2 presence. And what you do is induce a change in the solubility of one of the blocks. And one of the most desired consequences of that is that you can induce a reversible assembly and reassembly. So this is after the reaction happens and you've made your block copolymers, you can induce morphology transformations back and forth. And these are normally reversible processes. And by doing that, you can induce a wide variety of changes: swelling, deswelling, complete disassembly, reversible assembly. And you can choose to control the extent of this by, for example, varying the degree of cross-linking. So if you have a more cross-linked system and you had spheres, for example, or worms or vesicles, they may not be able to completely disassemble if part of the molecule is cross-linked. But if you wanted to be able to completely disassemble and reassemble them repeatedly, then you would ensure that you have no cross-linking in your reaction mixture. Here's an example of a CO2 switchable system from 10 and all, and they make this polymer shown in the top row first of all. So they take a PEGMA based RAFT agent, and then they add a water-soluble monomer, and then they have this diamina. And diamina is a tertiary amine containing monomer. It's also thermally sensitive, by the way. It has an LCST. And when you do this process, and they've done it here using irradiation at room temperature, you can make this type of block copolymer. And by doing this, you can have spheres, worms, or vesicles, depending on the relative amounts of each of the materials. And because you have diamina in there, and the tertiary amine groups are carbon dioxide sensitive, so you can induce morphology changes by introducing carbon dioxide into the system. The carbon dioxide will protonate the tertiary amine groups, and then you can have this reversible change in morphology. And you can remove carbon dioxide in these systems simply by sparging a system with air or nitrogen or any non-acidic gas to deprotonate the amine groups, and then you experience a reassembly from the dispersed materials back into the structures you originally had. And here's another example shown here from Levitt and co-workers. And in this case, what they have done is they've done a RAFT polymerization, and they've used functionality with having acidic or acrylic acid, carboxylic acid groups, really, on the terminus of the molecule. And these now give you pH sensitive materials. So you can undergo this type of vesicles type structure when you're at low pH. So pH is less than about 4. The acid groups are in their neutral or protonated state, but if you increase the pH, you will ionize the carboxylic acid groups, and you get this charge on the end of them, and then you get a change in morphology from vesicles into either worms or spheres at higher pHs. I mentioned earlier that you need to have some type of living polymerization to do the PISA reaction, but in fact it's quite flexible how you do it. RAFT is probably the most commonly used chemistry for doing RAFT or PISA, but people have also used ATRP, NMP, and even ring opening metathesis polymerization, or ROMP. So I'd like to now spend the last few minutes in the lecture and give you some examples of how you might do PISA using NMP and using ring opening polymerization. And these are examples from my own research group. So this was work we had done to make spherical particles. This was published in Polymer Chemistry. And we wanted to use nitroxide-mediated polymerization to conduct this. Now, we did this in one of two routes, first starting with the more simple route where we made a nitroxide terminated macro initiator, two-pot process, and then we refined it to allow a one-pot process, which I'll demonstrate in order. First the one or two-pot, and then moving on to the one-pot process. So if we're going to do a two-pot type process, what you need to do first of all is to make a macro initiator. So in this case we took diima, which is a sister monomer to diimima. It's the diethyl aminoethyl methacrylate. And we made a macro initiator using the NHS block builder. A block builder is the SG1 based alkoxyamine or initiator that Arkema sells. It works okay with methacrylates, but if you modify it with the NHS group, you get much more effective polymerizations. And to get even better control of the polymerization, you can add about 10 mole percent styrene, and that'll give you a very nice living methacrylate polymerization. So we made this polydiima macro initiator with a little bit of styrene in it, and that was the starting point for the process. And really what you need for an effective PISA process is to ensure you have a good living system, so all your chains are still functional so they can develop into the block copolymers that you want when you do the PISA step. And you can see here in this slide that starting out from a macro initiator at 16,000 molecular weight in the red, and then going to the green and the purple curves, that we can get up to about 55,000 molecular weight with a reasonable dispersity index. And this gives us good assurance if we look at the plots that we've got a fairly good living system here. Now you don't need to go up to that 21% conversion depending on what it is you're trying to do. You can be at much lower molecular weights for the first block, and in fact a lot of the work you'll see you may have molecular weights of the first block of down around 4,000 or 5,000. It really depends on your application. We wanted here to see how high a molecular weight we could go to and still maintain decent livingness. And what we learned was that with this system we can make fairly long initial blocks, macro initiators, and still retain a good living system. Now starting with that p-diima macro initiator, and you'll see in this example we did in fact use a first block, the macro initiator, that had an MN value of only about 5,900, so quite a bit smaller. And when we did the chain extension on it, we wanted to make sure we could do this effectively, and this was done in an emulsion polymerization type process. So this would be an example of what I earlier described as surfactant-free emulsion polymerization. The diima groups become protonated and the tertiary amines on them, and they function as stabilizing moieties. And the second block was a methyl methacrylate block, and we took its final molecular weight up to about 100,000. You can see a very nice chain extension here, which indicates a very high degree of livingness for these systems. So you can do a very nice PISA type process, and you do in fact make spheres. But we are also interested in whether or not we could do all of this in a single pot. And the incentive for this is that you don't need to isolate and purify the macro initiator. Now this requires more challenging polymerization with these particular monomers, and that requires an aqueous NMP with the diima. And for various reasons I'm not going to get into today, that can be more challenging than doing the bulk or solution NMP that we use to make the macro initiator that I described in the previous few slides. So in this scheme here, you can see again we're using the monomer diima with styrene. We use the VA044 initiator, a little bit of SG1 in there to conduct the polymerizations entirely in water. So we were able to make this initiating group in water as our first step. And then the second step we did in emulsion. So in this case we used MMA with a little bit of styrene for the second step. And again, for the same reason, we have a little bit of styrene that offers us good control of the growth of the second block. And when you do the emulsion polymerization in the second step, You do in fact form spherical particles. Polymerization proceeds nicely. If we look at the molecular weight distributions of the polymers we're making here, we start out with the macro initiator. This is the blue curve, and we see it has an Mn about 4,300. And being low molecular weight and being in aqueous methacrylate polymerization with nitroxide, it's not a very well controlled system. The dispersity is about 1.7, but it is a very living system. And you can see as we extend the second block out to higher molecular weights, and we get up to about 53% conversion with an Mn value of just over 100,000, the dispersity just keeps getting better and better. And the final molecular weight distribution we see shows a near complete shift of chains from the initial macro initiator, which indicates we have very good livingness in the system. And as you should always do with a PISA type process, you want to confirm your morphology, and we had a look at what we made by transmission electron microscopy, and we can see here that we have spheres. And normally when you have any type of PISA process, you're going to want to be looking at images. Any of the conventional light or particle measuring techniques, for example, dynamic light scattering, will not tell you anything about shape. So TEM, SEM, and AFM are the preferred characterization techniques for getting a sense of what shapes you have or what combinations or range of nano objects you're making in your PISA process. We've also done ring opening metathesis polymerization. In this case, what we did was we started out with a water-soluble monomer that we synthesized. So this was a PEG-modified norbornene monomer that we synthesized in the lab. And then we used a PEG catalyst, and I'll show the details of the synthesis of that later. So this gave us initially a water-soluble macro initiator. And then we added cyclooctadiene, COD. This is a water-insoluble monomer. And we were able to conduct the PISA process fairly well, and we end up with spherical type particles. The key thing here is coming up with a water-soluble PEG catalyst. And those of you familiar with ROMP may know that in the early days, ROMP catalysts were very moisture sensitive, very intolerant of even polar monomers, but there's been a lot of progress made. We started with a Grubbs second generation catalyst. The first thing we needed to do was put a ligand on it that was water soluble to make the whole catalyst water soluble. So we took a functional PEG group, we tosylated it, and we ended up with this ligand here. We reacted that with a second generation Grubbs catalyst, and this gave us a catalyst now that was ruthenium based, that was completely water soluble, and it led us to the first step of the PISA process in water. So just to refresh you on what we're doing here, we have our water soluble monomer, and now we can polymerize that with the cyclooctadiene, and what we're trying to do is make a block copolymer here with the PISA process. And I just want to leave you with a couple of thoughts about this, and this illustrates the importance of the ratio of the blocks. If we look at the first yellow column here, this is the norbornene PEG to COD ratio, and the norbornene PEG monomer is the water soluble one, and the COD is the water insoluble. And you can see that when we have a low ratio of norbornene PEG to COD, we don't even get particles. We get something very, well maybe, but they're very, very large. They're more like large, irregularly shaped aggregates. As we gradually increase the ratio of the norbornene PEG to the COD, we start moving down into a region here in experiments 3, 4, and 5, where we get, first of all, very large particles, but they keep coming down. So in order to add to a 30 to 70 ratio, we're now getting into the realm where you're making about 200 nanometer particles. If we look at the PDI value for experiment 5.04, it's very nearly monodisperse. And we do get full conversion at the end of it, although not full conversion of the first block, but about 75% conversion of the Norbornene block. And that just really illustrates how important the ratio of the blocks is in determining not only the shape you get, but the size of the individual nano-objects that you're going to be making. Now just focusing on experiments 3, 4, and 5 from those RAFT experiments, if we look at on the left column the GPC traces and on the right column the particle size distributions, you'll see that as we, just to go back, as we change the ratio of the PEG Norbornene to the COD, and as we keep increasing in order from experiments 3 to 4 to 5, not a huge change in the final molecular weight, but we see a dramatic change in the particle size distribution, and getting down to, at the bottom right, about a 200 nanometer particle narrowly dispersed for that ratio where we were seeing the best overall performance. So some concluding remarks. PISA is a highly versatile, simple route to make block copolymer structures that are not easily made by conventional routes. The key enabler is that you're doing a living polymerization. You can make a diverse range of morphologies and architectures with PISA, and you have the flexibility to incorporate stimuli-responsive and/or reactive functionalities that enable reversible switching of the morphology in response to triggering one of the functionalities that you've built into the structure. And while this is an active field, it is certainly not mature, and there are many exciting developments to be discovered, and hopefully some of you will be involved in some of those discoveries. I hope you found this lecture instructive and useful, and I hope you enjoy the rest of the conference. Thank you very much.